All right. Welcome, everyone. Thank you for coming. My name is Victor, and we're going to spend the better half of an hour talking about regular types. So why regular types? Why do we need to talk about this? Why aren't we talking about cool template stuff? Anybody know the yellow thing there behind the lambdas? Something coming very soon in the standard. Template lambdas. We're not going to talk about any of that cool stuff. We're going to talk about boring old stuff. What I consider fundamental principles for programming, the elements that we based our assumptions on, and the building blocks for understanding and communicating intent between different components in a system. So this talk is not just about regular types. It's a moment to reflect on STL and its design principles as best described in the seminal paper from 20 years ago by Alexander Stepanov, Fundamentals of Generic Programming. So we're going to cover a lot of topics. Of course, we're going to examine what regularity means. We're going to talk about how regular types naturally appear as a necessary foundational concepts in programming and investigate the requirements on using types and defining our own types and defining data structures and working with built-in algorithms and composing these in our programs. So not just regular types, we're going to spend some time on what values are. If you've been in Herbstadter's talk, you've certainly heard that values are the values of C++ programmers. So these should be important for us. We're going to talk about objects, but not as in object-oriented programming, as in what objects are in memory. We're going to spend some time on concepts, ordering relations, and requirements on types. But first of all, who have seen this talk by Titus Winters at CPPCon? It's a two-part talk, so I see a few hands. Too few. Do follow the YouTube links and watch them. I'm going to focus on part 2, that I think it's very relevant to what we're going to talk about today, and about type properties and what properties can describe types and what combinations of properties are useful and good in type design. So before we start, we need to build up some kind of a vocabulary such that we understand each other and know what we mean. Some of you have been in Kevin Henne's talks earlier, so we definitely need to get a good understanding on the semantics and what we mean when we say, for example, value or object. So we'll start with the very basic. A datum is a finite sequence of zeros and ones. A value type is a correspondence between a species, abstract or concrete, and a set of datums. A value is a datum together with its interpretation function. For example, a 32-bit 2's complement big endian is its interpretation of that datum. So it's a value. And the value is a constant. It cannot change. The value 5 in its representation that we have chosen, it's a constant. It cannot change. On value types and equality, we need to be very strict here when we build up our assumptions and what do we mean when we work with values. A value type is uniquely represented. If it's uniquely represented, equality implies representation equality in memory. If a value type is not ambiguous, representation equality means equality. And we're going to spend some time today talking specifically about equality and what it means to define equality. And we'll see that it's not such an easy concept to define. An object is a representation of a concrete entity as a value in computer memory, defined by its address and its length, and as we've seen in the representation. And it has a state that is a value, and this state can change. So its value can change. The value of an object in memory can change. A type is a set of values with the same interpretation function and operations on those values. This is just a formal definition, and a basic one. And a concept is a collection of similar types. And as Kevin said earlier, it's all about predicates. It's predicates all the way down. Concepts are predicates on types, types are predicates on values, and so on. So it's all about predicates. And we're going to see quite a few predicates today. Anyone know what EOP means? EOP, a few hands, yeah. Is this book. Yeah, it's a foundational book, I think, one of my favorites. I would be lying if I told you I understand everything in that book. So I keep reading it. So it lays down the foundations for basic concepts and elementary types and elementary notions that we need to understand as programmers. And I definitely think this is not a beginner's book, but a more seasoned programmer would find truths in there. And I know I had a few aha moments reading chapters of that book after years of programming. So I definitely recommend that you keep that one on your desk. More complicated acronym there. FM2GP. Marshall knows, yeah. So it's this one. Now, this is one that I would confidently recommend to beginners, and I often recommend it to students. It's a good segue from foundational things that we learn in STEM and in general in mathematics. High school mathematics is not very complex mathematics. And it's a progression, it's a nice historical evolution and follows various mathematical breakthroughs and the evolution and refinement of algorithms, specifically, for example, GCD, over time as we grew our collective understanding of mathematics. And it's all from this person, Alexander Stepanov. And where am I going with this? My purpose is to prove to you that mathematics really does matter. And for example, I recently discovered an older video, a presentation from Alexander Stepanov, but very recently published to YouTube, I think. And it shows how a very simple algorithm is a nice addition to the book, for example. You can follow a very simple algorithm like GCD and its evolution over 2,000 years and see how it shaped mathematics and refining and generating new concepts and generalizations on this very simple algorithm, and how we got here from basically from the Egyptians up through modern day mathematics and computer science. And mathematics, yes, it really does matter. And mathematics is something that allows us to coherently communicate about our intent and specify phenomena in nature and formalize our expectations and rigorously reason about algorithms and how we structure our work. But you may say that, yeah, I've been programming for 15 years now, and I didn't need any math to do that. So it's fine, thank you. I'm okay. I don't need to know more than I've learned in high school. So first of all, I don't really believe you. And the reason that things that just worked for you is because others have thought long and hard about these concepts for you. And they've designed types that make sense, and they've designed algorithms that are intuitive and easy to use, so you don't have to reinvent the wheel every time you want to sort a collection, for example. So mathematics really does matter, and it matters to you as well, even if you're not a library developer, because you need to match the expectations of the library designers and understand the preconditions for particular constructs and their expectations and the semantics of the types involved. And if you play nice with the library, you will get the expected results, and it will feel intuitive and easy to use to you. If you do not understand the rationale behind it and you don't play along, you will have surprises. So just because a library is out there and used by millions of people, it doesn't mean you cannot misuse it. So it's all about natural and intuitive use. So stay with me. I'm going somewhere with all this. So I do recommend a series. It's a long series, so only for the very passionate of you. But if you do have the time, it's a fantastic series, 3 algorithmic journeys. It's all on YouTube. A series of presentations by Alexander Stepanov at A9 right before he retired. And it's all about this long journey. And it's full of nice stories and historical vignettes and mathematical truths and useful applications in programming. And if you do have this inclination and the time, because it's quite a long series, I do encourage you to follow that. I know I enjoyed it. So right from Spoils of the Egyptians, about 10 hours worth of video, I warned you. Error of Pythagoras, division with remainder algorithms, and up to modern mathematics like Peano axioms and the relations with the natural number series. And lots of interesting stuff with arithmetic and infinite series and more mathematics. And it all leads up to this. So this whole preamble was for this paper, Fundamentals of Generic Programming, about 20 years ago. So generic programming depends on decomposition of programs into components which may be developed separately and combined arbitrarily, subject only to well-defined interfaces. Oh, that's a mouthful. Among the interfaces, this is the interesting part. Among the interfaces of interest, the most pervasively and unconsciously used are the fundamental operations common to all C++ built-in types, as extended to user-defined types, and operations like copy constructors, assignment, equality. What does this all mean? It means that when we define our own types, if we make them behave intuitively and uniformly, for example, if our types behave like ints do, or in terms of initialization and comparison and value semantics, then most of the expectations of our users of our code will be met, and we'll have a very smooth intercommunication or liaison between components as they satisfy expectations between each other, users and implementers. We must investigate these relations that must hold for these components to preserve consistency and semantics to meet these expectations. And we'll see how we can go about doing that. We can produce an axiomization on operations based on consistency, intuitive use, expectations, in true mathematical form, not just vocabulary. In other words, we need a foundation powerful enough to support any sophisticated tasks, but simple and intuitive to use by beginners, for example. I don't need to be an advanced user to understand your code. But is simplicity a good goal? Is it something that we need to strive for? We're C++ programmers, aren't we not? I think we have a foolish pride in our industry in thriving in complexity. And for this, I'll point you to a wonderful keynote by Kate Gregory from 2017 at Meeting C++ about simplicity, and is simplicity a good goal for us, and what we should strive for. So simpler code is more readable code. Unsurprisingly, code is more maintainable. Code that moves complexity to abstractions has fewer bugs oftenly. Think vector or RAII. Compilers and libraries are much better than you most of the time. Simplicity requires knowledge. So it's not something that should be assimilated with lack of knowledge. More, it should be assimilated with being wise and having experience and understanding why simple things are important. Simplicity is an act of generosity to others, to future yourself. It's not about omitting stuff or partial truths or simplicity or skimping out. It's about being sincere and explaining stuff from basic principles. And I'll get to a fairly recent article. Anyone read by any chance this article by Titus Winters? Okay, a few hands. So, revisiting regular types after 20 years. So this article evokes the Anna Karenina principle for designing C++ types. Good types are all alike. Every poorly designed type is poorly designed in its own way. So this is an essay both on, it's a very good synthesis of the original paper by Alexander Stepanov that I mentioned earlier. So if you have difficulty following through the original paper, this is like a Reader's Digest version of it. So it's a good synthesis, and it's very up to date in terms of analyzing recent additions to the standard library and the efforts of evolving it further, and what it means in relations to expectations and specifically to regular types and non-values. So it's definitely one of my favorite go-to resources. And if you take away anything from this presentation, is that this might be the paper might be the essence of what I'm trying to deliver here, with examples, of course. So it gives us the basis to analyze working with non-owning reference parameter types like string views and span without discarding regular design. So although these types might not be regular as per Stepanov regular, as we'll analyze further today, it gives us some footing into confidently talk about these recent additions and be confident that we're using them right. So let's go back to the roots, STL&S design principles. Again, another resource if you do not like reading long mathematical papers. The video version is up there. All my slides have links, so if you get them afterwards, all the resources are properly linked. And I have a huge reference area at the end. So fundamental principles, let's go back to the basics. Systematically identifying and organizing useful algorithms and data structures. Finding the most general representation of algorithms. Using whole part value semantics. And I highlighted this bit because this is what's of interest for us today. Using abstractions of addresses as interfaces between algorithms and data structures. Think iterators or ranges. And algorithms are associated with a set of common properties. For example, associative operations like plus, multiply, min, max. We can reorder operands, we can parallelize and reduce based on this property of the operation. And it's like I mentioned earlier, it's a natural extension of 4,000 years of mathematics from GCD up to this moment. And the thing that there is a generic algorithm behind every while and for loop. And of course, I don't have to say that the famous, it's obviously a rotate here, but it usually is, although not always a rotate. Sometimes it's a find. Okay. STL data structures. They extend the semantics of C structures in terms of memory layout. Two objects never intersect, and they should have separate entities and separate lifetimes. Copy the whole, copies the parts. We usually don't obey to this guideline. When a whole object is destroyed, all the parts are destroyed. Two things are equal if they have the same number of parts and their corresponding parts are equal, and all the way down, recursively. We fail to do that as well, sometimes. And yeah, it's all nice and good, but it does come with some drawbacks. For example, sometimes we have an abstraction penalty, although nowadays that's more rare. We have the implementation interface. In the interface, we want inlining, we want templates, we have to live with that. Early binding, sometimes horrible error messages because we don't have a formal specification of interfaces yet. Duck typing, and algorithms could work on some data types but fail to work on others, or further modifications in the data structures later on might break algorithms. And basically it all boils down to the fact that we need to fully specify requirements on algorithm types. And we're getting there very, very soon. I don't mean today, I mean we as a community. Maybe C++ 20, hopefully. So Some examples of named requirements. You don't have to go through all of them, but I am sure they're familiar sounding to you. Named requirements are used in the normative text of the C++ standard to define expectations of the standard library, exactly as I exposed in the introduction part. Some of these requirements are formalized as C++20 concepts. Until then, the burden is on the programmer to ensure the library templates are instantiated with the templates argument that satisfy those requirements. So we're not there yet. We're not on C++20, and we do need to pay careful attention on how we use our algorithms. And even if we get, when we get concepts, we need to be very careful when we define them, when we're composing them, because they're predicates. And as we've gotten accustomed to defining predicates for algorithms today, we would have to learn and practice this to understand the collection of available built-in concepts and how we play with them and how we compose with them and how we define our requirements, type requirements. What is a concept anyway? It's very complicated text there. A formal specification makes it possible to verify template arguments, satisfy expectations, blah, 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 blah. The important part, each concept is a predicate evaluated at compile time and becomes part of the interface of the template where it's used as a constraint. This is the important bit. So what's the practical upside? If I'm not a library writer, why do I care about it? I care about concepts. So if you're using STL algorithms and data structures, and I hope you do, then you need to understand concepts. If you're designing or exposing your own vocabulary types in interfaces and APIs, then you need to understand predicates and concepts. So I'll try to do a small segue here and tell you a story. I regularly visit my alma mater, and I give student lectures occasionally on STL and its design principles and using C++ STL for competitive programming. They have student competitions and ACM contests and stuff like that, and I sometimes teach there. And I always have a surprise here when I talk to students and I tell them about STL and algorithms, and they're sometimes surprised to use built-in algorithms and don't have the expected outcome when they're using them because they fail to understand the requirements on their types and how to properly use them. And it's nice when they get a compilation error because then they scratch their head and figure out what should I change here to make them work. But it's very hard when you don't get a compilation error, but you get unexpected results. Or even worse, sometimes it works, sometimes it doesn't, because you fail to meet the expectations or the expectations on the types and on the algorithms. So let's explore. This is how I start with them. Let's explore one popular algorithm, standard sort. This is their go-to algorithm, by the way. Of all the STL, that's the most important part for them. Vector and sort, and maybe for us too. So if we think about sort, we immediately get to a compare concept, which is basically a binary predicate, which is in turn a predicate, which is in turn a function object, which is a callable, basically. So this concept appears in over 50 STL facilities, algorithms, data structures, that expect some kind of compare type or comparable type. And we see here the definition of the algorithm. But what kind of ordering relationship is needed for the elements of the collection such that compare actually works? So this is the part where surprises appear for students. And yes, I know we have some squiggles that sound like high school math here, but bear with me. What's the ordering relationship needed? And we'll start with very basic stuff, stuff that we would expect that if we wouldn't obey to these rules, nothing will work, basically. So irreflexivity, anti-symmetry, and transitivity. Does anyone think this is not necessary, or the second one, anti-symmetry. If think instead of comp, think less than. If A is less than B, B must not be less than A. Does it make sense? Sounds reasonable, right? So if you need to internalize thinking instead of comp, think less. Or, I'm getting there. I'm getting there. You know where I'm going. Okay. So this will be anything less than this would be nonsense, basically. So we'll start with this, and we call this partial ordering, and we'll see if we can get away with it. Let's take a very simple example, like sorting a vector of strings. We sort with an implicit predicate. We specify less. We sort by specifying a lambda and using the less operator on the standard string. And then we do a case-insensitive compare. Very simple, very intuitive. Students have no problem understanding this. They expect it to work. It works. Nothing surprising there. All right. Let's take a slightly more complicated example. For example, think 2D points, a collection of points in a vector, and sorting the points. And think about a predicate like this one. I've actually seen this from students. So, does this work? Does this sort the points? Why? Yeah, basically, Marshall boiled it down for us. Yes, but they don't see that. It's not obvious. You don't get a compilation error. It's just about your assumptions about the types and how you build up your predicates. So actually building up predicates for such a trivial example, such a 2D point, what can be more simpler than that? It can get messy. So I always try to use pictures. It's maybe this way everybody can understand. Some people are visual in terms of their cognition and understanding. And if we take a very simple example, we can see that we can establish a clear relation between P2 and P3 because both their x's and their y's are in less ordering. But we cannot say anything about P1 and P2 or P1 and P3 because one has a greater axis and one has a greater y-axis. So we cannot, by that predicate that we chose, we cannot say anything about that relationship. So it's undecided. So we say P1 and P3 are ordered. That's why I display in green. And P2 and P1 and P1 and P3 are unordered with regard to the chosen predicate. So we cannot say. For us, they seem equivalent. So if we define equality, or equivalence, sorry, as being our compare predicate is false for both AB and BA, exactly the situations we have for P1, P3, and P1, P2, then we say P2 is equivalent to P1 according to our predicate, P1 is equivalent to P3, and P2 is less than P3. So this is definitely not a good predicate for sorting points. It will not get an unexpected result of any kind. Okay, so partial ordering seems not to be enough. Compare needs a stronger constraint. Let's see. The next available one will be partial ordering plus transitivity of equivalence, because we've seen equivalence creep up on us as we analyzed a very simple example with some numbers and points. So if we think about equivalence, we immediately have to think about transitivity. Does it have transitivity? Do we want that property? So if we define equivalence as we've seen before, comp A and B and comp B and A both being false at the same time, then we add one more row to our requirements table, and we say we want transitivity of equivalence, which means exactly as we think. If A and B are equivalent and B and C are equivalent, then A and C are equivalent. Then we can go even further and we say total ordering relationship comp induces a strict total ordering on the equivalence classes determined by equiv function. And we can say it another way, the equivalence relations and its equivalent classes partition the elements of the set that are totally ordered by less than. If we think about, instead of comp, we use the less than, because it's easier for us mentally. And if, for example, we think about integers and comparing integers with less than, so we can define total order relationship like that. And we can write slightly different predicate. Here I'm writing it as comparing the distance from the origin of the Cartesian coordinate system. Is this a sufficiently good predicate? Is this a sufficiently good predicate? Does this satisfy all the requirements? It's not immediately intuitive, but if you go by the table and try to verify all the requirements, in the end, it meets the requirements. It's a funny predicate, but at least it's consistent. So this is what we're after: consistency. We don't lie to the algorithm. These are ordered like this, then we change our mind, then when we compare equivalent elements, we answer differently in the predicate. So if we're consistent, the algorithm does what we expect. We can change it a little bit and say we compare x's first, then we compare, in case of, so we have two ifs that compare x's, and if we reach this return statement, it means that the points are equivalent on the x's criteria. Yeah. So in case of equivalence on x, then we compare on y. So this means we compare by parts. Is this a good predicate? Good. I see a few nods. What's this called, comparing by parts? Lexicographical compare, exactly. So this is something we're accustomed to. But sometimes it's difficult to recognize it in other forms, such as structures or pairs or tuples. Yeah. This is what tuple does. This is what pair does in standard library. If you think about our 2D point, you can think about it like standard pair. So this is a good predicate. So the general idea is to pick an order in which to compare elements by parts, like we've seen. This is called dictionary order or lexicographical order. This is what pair does in its 6 comparison operators. This is what tuple does, and so on. Okay. Now, getting back to named requirements, I've highlighted a few of interest for us today, like constructible, equality comparable, less than comparable. This is something we need to focus on. So, we can define semi-regular, and again, it's a definition. We have to accept that. As being default constructible, move constructible, copy constructible, move assignable, copy assignable, swappable, and destructible. This would be a semi-regular type. Okay, this is just a definition. Cannot contradict me there. Okay. Now, if we want to define regular, this is where things get hairy, because we have to add equality comparable, as in regular, as in Stepanov regular, going back to the 20-year-old paper. So we'll see that equality comparable is a much more difficult requirement to define precisely for types, especially if we think about modern additions to the library. So STL assumes equality is always defined, or at least an equivalence relations. So something like a more relaxed thing than equality. And STL algorithms assume regular data structures. Again, going back to the foundation of the library and its design principles. And for example, if we transcribe the previous requirements table from comp, we switch to less than operator. So this is the only replacement I've made. We have the less than comparable predicate that has these requirements. Yeah, and we defined equivalence in terms of A less than B is false and B less than A is false. As I've told you previously to think about mentally when you're seeing comp there. So this would be our less than comparable requirement. Then if we go to equality comparable, we have to think about reflexivity. Is A equal to A? Yes. Symmetry. If A is equal to B, B is equal to A. Sometimes people overlook that. Transitivity, of course, we want that for equality. And the types that must work with operator equal, and the results should have standard semantics. So we cannot attribute it, even if we're free to choose our own implementation for our types, we cannot make it operator equal do something else than actually checking for equivalence or equality. So we have to keep the standard semantics that is expected of us. It's not enough just to return a Boolean. And for types that are both equality comparable and less than comparable, the C++ standard library makes a clear distinction between equality and equivalence. So this would be a formal definition of those two. And of course, equality is a special case of equivalence. Okay. Logicians might like to express things a little differently and say that we can define equality of two values if any predicate applied to those values yields the same result. But this is intuitively very simple to understand, but has no practical application because we cannot define all possible predicates on our values. So this is a purely mathematical view and something that if those values behave the same in all circumstances, we can certainly say that they're substitutable to each other, so they're equal. But this has no practical application for us. So defining equality is kind of hard sometimes. And even Stepanov proposes a definition that is kind of squeaky, I would say. Two objects are equal if their corresponding parts are equal, applied recursively, including remote parts, but not comparing their addresses, excluding inessential components, and excluding components that identify related objects. So it's difficult, especially if we think about objects containing pointers and references to other objects, and can get ugly. And now, mandatory slide. Let's gauge a little bit the audience. Who here is still on old C++ for various reasons? One hand. C++ 11. Library implementers don't count, Marshall. You do need to support that config. 11. Few hands. 14. More. 17. Wow, that's a good audience. Excellent, excellent. Okay. Sneak preview then. We have the spaceship operator in C++ 20, and this is a perfect example of being consistent in comparison operations. So it does have a very important relations to the topics we're analyzing today. So this is a three-way comparison, and these would be the comparison categories for the spaceship operator. And you see words that concepts that we've mentioned recently, like partial ordering, weak equality, strong ordering, weak ordering. So all these things you must take into account if you're defining a spaceship operator, because it's not as simple as returning 0, 1, -1. So things are more complicated than necessary sometimes. So a thing to watch out for. So it's all about relationship strength. I mean, how precise can we be about defining less than or relations in general for our objects? So these numbers are a little bit dated. In San Diego, before the committee meeting, I counted 11 papers to fix the proposal for spaceship operator. I don't know how many are still in flight. Maybe other people here have more recent numbers. So it might seem like a trivial thing, Defining a generalized spaceship operator might seem something trivial. It's not. And there are various concerns here, like performance impacts of using the spaceship operator for equality. Sometimes combining all operations into one, it's inefficient if all I want is to compare for equality. For example, think of something simple like comparing strings. Comparing for equality for standard strings, first of all, you can compare the lengths and be done with it if their lengths do not match. Sorting strings lexicographically and providing a less than comparator is something that is much more expensive. So combining operations do have even performance impacts. It's not just about semantics, it's also about performance sometimes. And various corner cases of using this operator in generic code and templates, lots of corner cases. I've put up links that do have examples in them. I'm not going to go into detail here because time. There are considerations regarding default ordering, all kinds of issues. Some of them have been addressed in the standards committee. And of course, potentially applying this operator on data types in the standard library, because people would like to see, for example, the spaceship operator for strings, for, I don't know, string view, optional, span, I don't know. Applying this and doing it in a way that doesn't break users' expectations, it's not a trivial thing. So, a slightly older tweet from Titus Winders: type design over time. You cannot safely infer semantics from syntax. Yes, true. So, I mentioned optional earlier. Anytime you need to express a value or not a value, or possibly an answer, or an object with delayed initialization, using a common vocabulary type for these cases raises the level of abstraction. We want this. We want to make it easier to express this without conventions. So if we introduce something that is standard, people know what to expect when they see it in APIs. So optional is it's good. Optional of T extends T ordering operations. This is why I'm mentioning optional in this presentation, because it's very relevant to the ordering relations that we've discussed. So optional of T extends T's less than, greater than, and so on. And an empty optional compares less than any option that contains a T. Another important distinction that it's necessary if we're storing or comparing options. So you can use it in the same exact context as if it were a T, because it meets these expectations of the programmer on the ordering relations of what's inside the box. So if we're thinking about a value or potentially a value inside the box, inside the context, if we're thinking about contexts, yes, it's a vocabulary type that allows to simplify code. Yes, it composes. We can use it to compose things. Yes, you can write way more error checking code, way less error checking codes, excuse me. So does anybody see where I'm going with this? So maybe a value wrapped in a box, that it's its context, that we compose, that we pass along. Yeah, Matthias said the M word. Yeah. So we can think about optional as a potentially monadic wrapper, and there are proposals. There is one from, I call this the Simon Brandt slide, or the M word slide, of course. So there is a proposal. Hope it makes it through Cologne in the next standards meeting. I know there's people opposing this, but I'm enthusiastic. I want to see this. That's my opinion. So monadic extensions and continuations so that you can easily compose optionals. So you can have this kind of continuation or data transfer and moving a value in its context along a stream of computations. I know I would like to see that. I'm still optimistic. What about optional of tref? Does anyone seen this? No? Too sensitive? Too soon? I've seen vicious arguments over Twitter on this. So yeah, there are people on both sides with very good arguments. So on this one, it's hard to pick a side because I've seen good arguments on both sides. So there's people that say that this is not something that you would like to see in the standard. There's people with very good explanations and use cases when this is useful. This one is a sensitive one. I'll leave you to be the judge of that. I'm not forwarding an opinion here. Okay. Yeah. And now we get to string view. This is again related to what we're talking today. Is related to the expectations, the ordering relations, the equivalence, the comparison, and it's mentioned in the paper that I said earlier from Titus Winters, revisiting regular types. String view and span coming in C++20 are very good targets for this analysis from all the considerations we've visited already. So everybody's familiar with string view? Some people? Okay. Quick summary then, because I don't see a lot of hands. So this is basically a class template describing an object that can refer to a constant continuous sequence of character-like objects. So it's basically a view, like the name says, into a constant sequence of characters. So maybe a partial view into a string or something like that, or some string literal. And the important bit here, I would say it's constant sequence. This is, I think, the important bit. And we'll have to make that distinction when we talk about span, because in case of span, that's not true. String view does not manage the storage it refers to. The lifetime management is up to the caller, and this is the tricky part. I have a whole talk only on string view. If you haven't seen it already, this is my shameless plug. Go see it. The purpose of the talk is not to scare you off using string view, rather raising awareness, because we've actually had types like that in C++ before, but I see the parallel with string view as being a go-to vocabulary type that is too available and too tempting to use in dangerous situations. So if you know the pitfalls and the gotchas, like everything else in C++, you're fine. But you do need to know the context and be aware of the parallels. So it's a good class. The name is misleading there, but you do need to know the gotchas. Does anyone recognize this? Yeah. Yeah, we're actually in the room that's called SS Great Britain here. So we have pretty pictures of the vessel there. So yes, it's Brunel's SS Great Britain, here in Bristol. Does anyone know the relationship between string view and the keel or the bottom of the Brunel's ship? Can anyone guess where I'm going with this? I've actually visited the ship a few days ago. I took this picture. There are signs there in the ship's museum about this. I'll give you one more hint. Rust, yeah. Okay, so string view is a borrow type. It's going back to the owning semantics, and we'll get to the relationship and the equality very soon. String view is basically a borrow type, and it succeeds admirably in the goal of drop-in replacement for a const string reference in parameters, for example, and that would be the premium spot for its usage. The problem is that traditionally we have been accustomed to two kind of things in C++, like object types and value types, things that are references and things that are values. And this is a new kid on the block. It's something that it's not an object and it's not a value per se. It likes to pretend it's a value type when it actually is a kind of a reference type. So this is where all the gotchas and perils come from. If you're thinking about it like it's a reference, but it's the kind of reference that doesn't extend lifetime, then you understand the perils. If you're using it as a regular type and ignore that aspect, and you can use it as a regular type without compilation errors, then you get into trouble. So borrowed types, as Arthur defined them, the terminology is borrowed from Rust. So they lack ownership, they're short-lived, they generally can do without an assignment operator, although for string view we have one. They generally appear only in function parameter lists. They generally cannot be stored in data structures or returned safely from functions because of the ownership semantics. And this is where the perils lie for string view, for example. So string view is perhaps, like I said, the first mainstream borrow type in C++. So this is why I see it as my duty to warn people about using it. It is assignable, so this is where the peril comes from. Assignment has shallow semantics, and viewed strings are immutable, which is an advantage. Meanwhile, the comparison has deep semantics. When we compare string views, it compares the underlying buffer, the underlying character arrays. So it's a little bit weird in terms of formal specification, what it is to be actually regular, as in Stepanov regular. So it's a little wacky. So string view is a non-owning reference type. When the underlying data type is extant and constant, we can determine whether the rest of its usage still looks regular. So one advantage is that it's constant. The underlying buffer needs to be constant. And if it's extant and we can prove by construction that the thing that I'm referring to with this view, it's still around by construction, then I can squint a little bit and pretend it's regular. So I can use it as if it's regular. I can store it, I can pass it around and use it as if it were something like a value. But only if I can prove those things about its context. So this is where the most important thing is, when using types like ints and standard string, you can reason about them independently, outside their context. When you're thinking about types that are like string view, or worse, like span, you cannot analyze them in isolation. You have to think about them in their context of usage. Where am I using it? Where does this come from? What are the relationships? So generally, when used properly as a function parameter, for example, string view works very well, and you don't have unexpected results, and it behaves as if regular. So, but if you think about things like span, this is a very confusing type, and I've seen people that know a lot, have heard a lot more than me about this, have furious discussions around various little corner cases and details on span. So I'm following closely to see how this develops further. And I think we're still learning about using types like this, because again, span is quite a known as type. It's not like, hey, a pointer into a buffer or some kind. When I see a pointer, I know what to expect. I know I have to be careful. I have to think about what it means to pass it around, the lifetime, expectations, what it means to compare some memory regions. When I see span, I tend to think of it as something that it's a value. And that's wrong, I think. So span is think array view as in string view, but on mutable underlying type. So this is a fundamental difference, in my opinion. So people like to say that I already have string view. Span is just like that, only not for characters. It's not like that because the underlying type is mutable. So it's kind of like this. Yeah. So non-owning reference types like string view or span, we need contextual information when we're working with them. we cannot use and rationally analyze things without the context. Things you always need to consider is shallow copying versus deep copy, shallow versus deep compare, const mutability, and what it is to define operator equal on. So my call to action to you would be make your types regular. Always strive for that. And mentally think integers. Yeah, if my types are like integers, I'm okay. The best regular types are those that model built-in more closely and have no dependent preconditions. So think dependent preconditions being string view or span. So don't behave like that. Try to strive for something that doesn't depend on its context, so I can analyze and predictably say what this assignment means. So like I said, think int or standard string. For non-owning reference types like string view or span, because these types are necessary. My call to action is not don't use them. These kind of things are necessary. And we've been playing to these kind of things for years now, way before they were in the standard. So, but now that they've become part of the day-to-day vocabulary and they will show up in interfaces, we need to pay close attention and we need to educate ourselves and the community on how to use them. You need contextual information when working with them. Doing code reviews, it's not gonna be a simple operation. You need to examine the whole context, not just diffs. So you need to pay careful attention when using these types. Try to restrict them to semi-regular to avoid confusion for your users. So at least strive for semi-regular if you cannot achieve regular types. So that would be my call to action on this part. And preparing for this talk was most fun I've had in a long time. And mainly because of some excellent resources and excellent articles I've read on various topics related to what we've been presenting today. So I do encourage you to read their work. I've put references here. Everything is linked up. So when you get the slides, if you want to read up on them, there are various resources there. Regarding equality, regarding semantics and borrow types and span, string views, rules for regularity and proposals, and very good blog post on upcoming proposals and things we need to fix up. A very interesting series, very close to the first half of my talk, is actually a series of articles from Jonathan Mueller that actually presents slightly methodical and academical approach to defining the required mathematical relations and defining comparison and relations for types from the underlying mathematical representation. Slightly differently from what I've done, but I very much enjoyed this series of articles, so I do recommend them. So this would be why I care about regular types, and we have plenty of time for audience interaction if you have, or I have bonus slides, your choice. So if you do have questions or maybe something that you do not agree with, I'm open to that as well. Otherwise, I could have some bonus slides if you'd like. Questions? Yeah, sure.
Why would anyone be against the monadic extension to
I cannot answer that on camera because I can drop names, but not on camera. Yeah, we'll talk about that later.
What was the question again?
The question was why would anyone oppose monadic extensions on STD optional? Care to comment on that? No. Again, not on camera.
No, mostly because I don't have anything yet.
Yeah. Yeah. We can talk afterwards. Oh. Okay. Care to share that? On no. Yeah. Okay. My personal opinion on that is that I liked it. I like it, and I've recently started playing around and learning Haskell and thinking in terms of functional and composition, and I kind of like that trend. So it makes you think differently and organize your work differently and compose your computations slightly different. And it eases up error checking and percolates nicely. But it, again, my opinion. I'm not even on the standards committee, so. Any other questions or disagreements? Or suggestions? No? I have a few. Do we still have time? Yeah. Okay. I have a few bonus slides. Just a second. See. I made the mistake of marking them as skip in the presentation, so yep. Okay. So an interesting topic related to this would be object relocation. And remember how we defined objects as being values represented in memory, in computer memory. Again, not object as in OOP. Yeah. One particularly sensitive topic about handling C++ values is that they are considered non-relocatable in memory. And again, I'll point you to very interesting articles from Arthur O'Dwyer on this subject. So, in contrast, a relocatable value would preserve its invariant even if its bits were moved arbitrarily in memory. For example, an int 32 is relocatable because moving its 4 bytes would preserve its actual value. So the address of that value does not matter to its integrity. It's easy to understand, moving an integer. Yeah. We cannot always say that about every object that we define. And I've recently seen an interesting characterization on Facebook's GitHub in the Foley library. A conversation between Captain Picard and an alien. So the alien says, so this teleporter, how does it work? And Picard answers, it beams up people and arbitrary matter from one place to another. Alien says, is it safe? Yes, but earlier models were a hassle. They would clone the person to another location, then the teleporting chief would have to shoot the original. Ask O'Brien, he was an intern during those times. A bloody mess that was. So we're kind of accustomed to this in C++. So this kind of teleporting. So there are some deep fundamental things that you need to consider when thinking about relocatable values. And I know there are recent, I think there are proposals about this on trivially relocatable types, and there are some interesting write-ups. Some of them are linked in the slides on what it is to define object relocation. And C++ assumption of non-relocatable values hurts everybody for the benefit of a few questionable designs. So again, opinion piece. Not everybody agrees on the semantics of this. So, but it's food for thought. And if you care about these things, and you have to think about performance and implications of these things, it's sensitive. Only a minority of objects are genuinely non-relocatable. Objects that use internal pointers, objects that need to update observers, that store pointers to them. These would be some classes of objects that are non-relocatable. So this would be food for thought on actually trying to use and design relocatable types in memory. Okay, questions or opinions on relocation? Yeah.
Can you give an example of that last one?
Which one? Let me see. Last item. Yeah. Sorry about that. Objects that need to update observers that store pointers to them.
Yeah. My
No, something like weak pointer maybe. Or something, an object that has an observer that, when fired, updates state within them. Like, I don't know, like a kind of a cloning operation that stores a pointer inside another object when it's created, like a notification of some kind.
One example would be a lambda that takes this.
Sorry?
A lambda that takes this.
Well, good example, yeah. Yeah, good one. Something that
maintains a registry.
Yeah, like registering as in a directory of stuff. Yeah, sure. If you think like the traditional observer pattern, I have some hooks, some callbacks that when fired, I register stuff in my object. Like I store a hash map with some pointers of created objects, like Marshall said, something like that. That would not be trivially relocatable.
So also something that has callbacks outstanding?
Yeah, or think about deferred operations like lambdas that captures things by this and processing is later. And sometimes you may even lose the context, as in the object might be destroyed before the operation is completed. Things like that lead to designs that are not relocatable. They're fragile, but there are benefits. Any more questions? We can discuss off the record stuff like monadic extensions, if you like, but off the record. Any more questions? No? Then more time for refreshments. Thank you.